So, welcome to our class for today. What we have on the board is mathematical induction. It's an advanced mathematics found in higher institutions, universities, and polytechnics. So, in this case, the question says we should prove using mathematical induction that 1 plus 2 plus 3 continue like that. This is a series. The series continues to n into n squared plus n over 2. Second question says the summation of n, r equals to 1, r 1 factorial equals to, open bracket, n plus 1 factorial minus 1. So let's start by proving the first case. But before then, we need to understand the concept of mathematical induction. What is mathematical induction? It's a method of proving that a statement is true for every natural numbers. So that to prove that this statement is true for n equals to 1, 2, 3 continually according to the series. So to start, let's take the first one. We're having solution 1, 1 plus 2 plus 3 plus continues plus n equals to n squared plus n over 2. So let's prove the statement to be true for n equals to 1. For n equals to 1. So n you are seeing n in the series, I will substitute 1. So I'm having 1 plus 2 plus 3 continues. See, here we have n, I will substitute 1. Here we have n, here becomes 1 squared plus 1 over 2. If I simplify this expression, I'm having 1 plus 2 plus 3 plus continues plus 1 equals to 1 squared is 1 plus 1 over 2. So I add up 1 plus 1, that will give me 2 over 2, which is 1. So you can see it is true for n equals to 1. When you substitute n as 1, n is 1, at the end of the day we have 1. Therefore, it is true for n equals to 1. So if you try for n equals to 2, you can see it also proves to be true. So n equals to 3 will prove to be true. What happens to an infinite number of n when we don't know the number of n? So that will be our second step. Step 2. Assuming it is true for n equals to k. So n you are seeing n, I will substitute k into the series. Remember the series says 1 plus 2 plus 3 plus continues. See, n is not k, is equals to k squared plus k over 2. So since we don't know the number of what k is, so we assume it is true. That's the meaning, that's what we stated, that assuming it is true for n equals to k. So let's take this one as equation 1. So to prove the statement to be true, if n is k, we put n as k plus 1. So anyway, we see n will also substitute k plus 1, but not into the original expression of n squared plus n over 2. We are not substituting here, we're only substituting it on the left hand side. So we are having 1 plus 2 plus 3 plus continues plus k when n is k, and when n is k plus 1 is equals to. So what is the value of the expression when n is k? When n is k from equation 1 is k squared plus k over 2 plus when n is k plus 1. So if we simplify the right hand side, this will give us k squared plus k over 2 plus k plus 1 over 1, so that we can take the LCM. So when the LCM of 2 are 1, our LCM is 2. 2 into 2 is 1 times everything I have here, I will have k squared plus k plus 2 into 1 is 2 times what I have here, 2 into k plus 1. So if I open the bracket, I'm going to have k squared plus k plus 2k plus 2 over 2. So let's factorize by bracketing the first 2 and also the last 2. This will give us k squared plus k plus 2k plus 2 over 2. So in the first bracket, k is common. This will give us k into k plus 1. In the second bracket, 2 is common. 2 into k plus 1 over 2. So let's classify the two equal brackets as 1. This will give us k plus 1. Let's take those outside the bracket, which is k plus 2. K plus 2 over 2. So this expression is true for n equals to k, although it did not satisfy the original equation, which is k plus 1, k plus 2 over 2, did not satisfy n squared plus n over 2. So how do we express this to satisfy the original condition? Though this expression is correct, but it failed to satisfy the original condition given to us, which is n squared plus n over 2, because we are not having any k plus 1 squared in the expression. So let's simplify this further to see if it can give us the original condition. So I can write this as k plus 1 into k plus 2 can be written as k plus 1 plus 1 over 2. 1 plus 1 is 2, so nothing changed. I'm not trying to manipulate what I have to satisfy this condition. So this will give me, so let's expand k plus 1 times, let me bracket this, k plus 1 times k plus 1 will give us k plus 1 squared plus k plus 1 times 1 will give us k plus 1 over 2. So you can see at the end of the day, it satisfies the condition of n squared plus n over 2. So when n is k plus 1, I will have here as k plus 1 squared. When n is k plus 1, I will have here as k plus 1, which satisfy this condition. So it is true for n equals to k plus 1. So this is question number 2. Unlike the first one that has a series, this one doesn't have a series, so we need to create the series from the conditions given to us from here. They gave us r equals to 1 into the unknown number, r in brackets, r factorial, and at the end of the day, they have n plus 1 factorial minus 1. So we keep substituting r as 1 so when r is n. So for r equals to 1, I will have 1 into 1 factorial plus, for r equals to 2, I will have 2 into 2 factorial. Continue like that, see, for r equals to n, I will have n into n factorial equals to n plus 1 factorial minus 1. So this is now the series. So to prove the series to be true, we start by putting n equals to 1. So anywhere I see n, I will substitute 1. I'm having 1 into 1 factorial plus 2 into 2 factorial. Continue like that, see, when n is 1 now, 1 into 1 factorial equals to, when n is 1, 1 plus 1 factorial minus 1. So if I simplify my right hand side, I'm having 1 into 1 factorial, 2 into 2 factorial plus 1 into 1 factorial equals to 1 plus 1, that will give us 2 factorial minus 1. What's the value of 2 factorial? It's simply 2 times 1, that will give us 2. So I'm having 1 into 1 factorial plus 2 into 2 factorial plus, continue to 1 into 1 factorial equals to 2 minus 1 equals to 1. So 1 can also be written as 1 times 1 factorial, because 1 factorial is 1, it doesn't change anything. So I'm having 1 into 1 factorial, 2 into 2 factorial plus 1 into 1 factorial equals 1 times 1 factorial. So we can see it is true for n equals to 1. When you substitute n as 1, the beginning value is 1 into 1 factorial, the last value is 1 into 1 factorial, and then our result is also 1 into 1 factorial. Therefore, it is true for n equals to 1. Step 2, assuming it is true for n equals to k. Let's assume it is true for n equals to k. So anytime I see n, I will substitute k. So I'm having 1 into 1 factorial plus 2 into 2 factorial. Continues to, when n is not k, I'll have k into k factorial equals to k plus 1 factorial minus 1. When n is k, I'll substitute it as well. So this statement, we assume it is true for n equals to 1, because when we tried for n equals to 1, it is true. So let's assume it is true for n equals to k. So to verify this statement, we put n equals to k plus 1. So when you are substituting n equals to k plus 1, to verify the statement, you only substitute it on the left-hand side without putting it into the original expression on the right-hand side. So we're having 1 into 1 factorial plus 2 into 2 factorial plus continue like that till when n is k into k factorial plus when n is not k plus 1, k plus 1 into k plus 1 factorial is equals to, what is the value of the expression when n is k? When n is k, this is what we have. So I'm having k plus 1 factorial minus 1 plus, when n is k plus 1, k plus 1 into k plus 1 factorial. So let's simplify the expression that we have. So I can group these two because they have a common k plus 1 factorial. So this will give us, let me write the first expression, k plus 1 factorial plus the second expression, k plus 1 into k plus 1 factorial minus 1. We are keeping this guy on its own. So what is common from these two expressions is simply k plus 1. So this one implies k plus 1 factorial into, if I factorize k plus 1 from here, I'll be left with 1 plus, if I factorize k plus 1 factorial from here, I'll be left with k plus 1 minus 1. So if I add up, I'm having k plus 1 factorial into k plus 2 minus 1. Recall the value of n factorial. What is n factorial? N factorial is simply n into n minus 1 factorial. So since n factorial is reducing by 1, the original factor will reduce it by 1. So in that case, if you are having k plus 1 factorial, it simply means that the original factor is supposed to be k plus 2 if you are reducing n factorial by 1. So this will give us, this expression will give us k plus 2 factorial minus 1. If you look, this expression is correct, but it's yet to satisfy the original condition, which is n plus 1 factorial minus 1. So how do we do that? I can rewrite this expression as k plus 1 factorial minus 1. So you can see it is true for n equals to k plus 1. Therefore, it is true for n equals to k plus 1. So that is a solution to the two questions. If you have any observation, please make the comments on the comment section. Share, subscribe, and comment.